Hello, I'm Paul Savas, and this is InfantGuard, my engineering project. On average, forgotten baby syndrome causes 37 deaths per year, with over 1,000 casualties since 1998. This is because vehicles can heat up to 120 degrees Fahrenheit in as little as 30 minutes, and death for infants can occur as early as 107 degrees Fahrenheit. In most of these cases, it's just accidental. The parent gets busy and forgets their infant, and therefore they're completely preventable. My solution to this problem is to create a device that can detect an infant alone in a vehicle, and it'd be able to notify the parent of the forgotten infant, and finally, it'd contact emergency services if vehicle temperatures exceed a specific threshold while the infant is present. To aid in the design process, the following design requirements are put in place. Firstly, the prototype would need to minimize cost and be easy to use after initial setup. It would also need to be able to detect an unsupervised infant accurately and take appropriate action. Similarly, it would need to limit the amount of false positives and operate even when vehicle power was off. It would need to be able to notify emergency services with vehicle location and temperature autonomously, and require minimal modification to the car seat so that the design could be implemented across many car seat models. To help with the design evaluation, the following data points are taken. For quantitative, the cost, battery life in hours, number of false positives, and response accuracy. For qualitative, the ease of use and degree of seat modification. The testing procedure would be as follows: create a bill of material, install and set up the system in the car seat, record seat modifications required, then perform a false positive test before then performing an accuracy test. Finally, determining the battery life using a milliamp meter and recording the ease of use. For the false positive test, two specific tests were ran: 60 minutes with the parent present and the infant in the car seat, and 60 minutes with no parent and no infant. In both of these cases, a false positive was considered whenever the Arduino took some sort of action, say by sending the user a text message. To test the system accuracy, 3 specific scenarios were each ran 5 times. In all these cases, if the Arduino took the correct or expected outcome, a point was awarded. At the end, the total number of correctly executed situations divided by total number of situations times 100 created the system accuracy. 5 tests were ran with the infant present at a non-dangerous temperature, but no parent was present. In addition, another 5 tests were ran with the infant and no adult, starting at a non-dangerous temperature before increasing to a dangerous one. Finally, 5 tests were ran where the infant was present and no adult, and the system was manually disabled. During the prototype construction, the first major step was to establish the key components and design choices. One way I wanted to detect whether the parent was going to be present or not was with a small Bluetooth device attached to their car keys. That way, if the parent left, they would most likely take their car keys with them, and it'd be easy to detect their presence or not. To do this, I used a BLE iBeacon and, on the Arduino, an HM10 Bluetooth module. To measure the temperature, I used a DHT22 temperature sensor, and to give the Arduino its cellular capabilities, I used a Botletic SIM7000A. The Arduino being used is an Arduino Mega 2560, and to detect the infant, I used a force sensing resistor. Finally, to manually reset the button, I chose to use a push button and a Belkin power pack to power the whole thing. Once that was out of the way, I created an outline of the code flow, and then I created the circuit and wired it in the breadboard with the Arduino 2560. Let's take a generic look at the code flow. The code always begins by checking for the child with the FSR sensor. If a child is detected, it'll get the location before completing a temperature check and doing a Bluetooth scan in search of the Bluetooth fob. Using those 2 answers, it's going to determine which type of response to take, whether it needs to text 911 or the parent, and which type of text to send. It's also going to check whether 911 has been texted in the last 15 minutes or the user in the last 90 seconds to prevent spam texting. Getting the Arduino to be able to communicate with the user's phone required a slightly more complicated workflow. The Arduino Mega and SIM7000A would establish a connection to a local cell tower via a hologram SIM card. Then, the SIM7000A and Arduino would access a very specific webhook.site URL. The key here being that the URL has built-in parameters, like the vehicle's location and temperature. Webhook.site will then redirect that information to a Cloudflare worker, which is a secure cloud computing service. Then, the Cloudflare worker will use that data to communicate with the Twilo API, and Twilo, on the Arduino's behalf, will deliver the message to the user's phone. On your left, you can see the car keys with the Bluetooth fob on top, and on your right, you can see the FSR sensor, that gray rectangle, where the child's back would be under the seat cushioning. Here you can see the child car seat, and in front of it, the prototype. The big black rectangle is a 10,000 milliamp hour Belkin power pack. This allows it to be plugged into the Arduino, giving it power, but also be plugged into the car's power source. That way, whenever the car is turned on, it'd also be charging itself. Here's a look at some sample text messages for each scenario. Looking at version 1 results, the one-time cost was around $220, while the monthly subscription fee was around $20. That was for the Twilos messaging fee as well as the webhook.site subscription. System accuracy was 80%, getting 100% on all tests except the manual button press, which got a 2 out of 5. There were 21 false positives, all of which occurred when the guardian wasn't present with the infant in the vehicle. Battery life was roughly 82 hours, and just to put this in perspective, the battery life can get to a full charge in only 4 hours. There was little degree modification to the seat, just needing to wire the FSR sensor. The button was hard to use though, and didn't always work. There was also just a general lack of status notification. The user didn't know whether the system was deactivated or not. And finally, the seat couldn't easily be removed without fully unwiring the whole FSR sensor when being removed from its dock. In other words, too many false positives and the button wasn't working. For the version 2 redesign, I started by adding a boot up text notification. I also changed the scanning logic for the Arduino to scan for the fob 5 times, and if it was considered present in at least one of those searches, then the whole search was considered positive. I also used attach interrupt with the Arduino to ensure that the button status was constantly being checked. I also added deactivation and reactivation text notifications, and I added connector clips so that the FSR sensor could be disconnected before removing the car seat. Here's an example of the better status communication messages. Look at prototype 2 results. The only major seat modification was gluing the FSR sensor once again. The system was much easier to use, especially with the deactivation and activation notification text. The button worked with no problem, and the connector clips made removing the seat much easier as the FSR sensor could be disconnected, though the user could forget to add them back. The cost and battery life remained roughly the same, and there were 0 false positives, while the system accuracy did take a toll at around 33%. The manual reset button worked normally, though the rising temperature and no parent test both got a 0 out of 5. This because the system was still detecting the Bluetooth fob present, even when placed 6 meters away. To resolve this issue, I designed version 2.1. Using the RSSI value of the Bluetooth fob, I was able to determine how close the parent was. The RSSI value is a signal strength, and I decided that if the RSSI value was less than -80, then the system should consider the parent not present. I would scan 5 times, and if at least 4 times the scan considered the parent not present, then the system would take action and altogether consider the parent not in the vehicle. I also added a second FSR sensor for redundancy, just in case the infant was moving around. Here are the version 2.1 results. As you can see, the cost and battery life remained roughly the same, with a 100% system accuracy and 0 false positives. The degree of seat modification was the same as last time, just gluing the FSR sensor. The system was easy to use. The only major problem now was that the wiring was a bit of a mess and could easily be disconnected. Also, the user could forget to plug the FSR sensor back in when redocking the chair. For the V3 redesign, I created a more permanent fixture to mount all the sensor and Arduino cables by putting them on circuit boards. Then, I also created a box to hide all the Arduino internals and with a little mounting for the button and temperature sensor. Then I also created a docking system for the FSR connectors, as you can see in the above picture. This would allow for each FSR sensor to have their own male and female connector, and that way whenever the seat would be placed down, the FSR sensors would automatically connect. This would make it much easier for the user to be able to connect and disconnect their seat. And this is once again 3D printed. Here's the final circuit schematic. As you can see, all key components are listed. Looking at version 3 of the prototype, the degree of seat modification was significantly more, including needing to mount the FSR connector at the rear of the seat and attaching the prototype case next to it. Ease of use, though, was much better as the seat could easily be removed or reattached to its dock without needing to manually connect the FSR sensor. Cost was $232 one time, system accuracy 100, number of false positives 0, and battery life 81. Here's the final list of my prototype materials. As you can see, both hardware and software is listed. Comparing all the prototypes tested, while a steady cost increase can be seen, so can a performance increase. From version 1, which had considerable false positives and suboptimal response accuracy, version 2 helped reduce those false positives while taking a toll on response accuracy. From then, version 2.1 and 3.0 helped give an 100% response accuracy and bring number of false positives to 0. Finally, version 3.0 helped significantly increase the ease of use with a docking component. Notes about some possible errors. First of all, the prototype would be much cheaper if mass-produced, since much more infrastructure would have been in place to support such a project. Furthermore, it's very hard to test true infant behavior without using a real infant. And lastly, it's very hard to quantify code, since code is very much binary, whether it works or doesn't. Nevertheless, this was still a massive learning experience, from learning the value of component testing to also learning the balance between performance and cost. Finally, hardware and software integration is much more complicated than people make it seem. For a more in-depth look at the project files and code documentation, please refer to the links below. I'd like to take a moment to acknowledge the Great Mills High School STEM Academy, as well as my family, for their continued support. I'd also like to acknowledge Mr. Simon Fredstead from Hoboken.site for providing me with a pro license. Here are my references. Thank you very much for your time.